Hello.
Hello, hello, good afternoon, everyone here.
Yes.
I welcome our chief guest, Dr. S. Das, sir, and he is working in government college, Orissa. So now I hand over the session to sir. Sir, you continue, sir. Sir, you start the session, sir. Sir, sir, you continue the session.
Hello. I think you are today. It is start for I think. So I'll be talking about smart grid. Basically, what is smart grid? And some network problem. But कौन बोलूँ network problem? Is it okay now? So I think the last class, the last sessions I talked about IoT as your ATAL FDP is based on IoT for smart grid. So if it's in present scenario, use anything you need the IoT. So first I will talk about the electric grid, why it is essentials. First half an hour I will talk about the electric grid. Then I will talk about the issues in the electric grid. Then I will be talking about the AC/DC microgrid. Then finally I will be talking about the electric vehicles. Sandano, कैसे हो? ये every day खुली हुई एक है. Present now, अपना. तो interest in अपना. अरे? अपना? पूरा अच्छी. एक मिनट. So I'll be talking about the smart grids. So there we will be discussing about the role of renewable energy. is it visible? Hello? Visible? Hello? Is it visible? Hello? 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 I am sorry for disturbance. There is some problem in the networks. Due to that, I was disconnected for some times. So, can I start now? Yes. So, I was talking about why we need a smart grid. What are the motivation for a smart grid? So, smart grid, if you say, is a desire. It will say it desire to make the grid smarter, safer, reliable, and more cost-effective using advanced sensors, communication technology, and distributed computing. The smart technology, if you see, it is basically using meterings, communications concerning grid operations, status, and distribution automations, integration of smart appliances and consumer devices. So yesterday, I think the last video we might talk, there are a lot of speakers may talk about the IoT. So that is Internet of you will see things. So there, this smart grid, they can tell smart grid tools. They have a lot of influence to use the IoT. Basically, smart appliances and consumer devices. You talk about your home automations, washing machines, all can be used by using the internet. So, deployment and integration of advanced electricity storage and peak saving technologies, which including plug-in electric and hybrid vehicles and thermal storage air conditioning. So with smart grid cycles are energy generation, storage options, power quality, self-fillings, electricity market, demand response, and energy efficiency. So how smart grid works? In general, working of smart grid technology can be understood by grouping into following key areas: integrated communications, sensing measurement, smart meters, phase measurement units, advanced component superconductivity, advanced control and pricing mechanisms, distributed generations, energy storage, electric vehicles. So if you see all those applications, you talk about electric vehicles, you talk about PMU, that is phase measurement unit, you talk about sensors. So all those things can be used with the help of internet. So this IoT plays very important to control all those things. So smart grid, if you see what is the summary, it keeps track of all electricity flowing in the systems, capability of integrating alternative sources. You just have keeps track of all electricity flowing in the systems and is a capability of integrating alternative sources, uses multiple networks and multiple power, generation company with multiple operators, which is implying provide bidirectional metering. As you know that in smart meterings, as I told in the IoT, when I am talking about IoT for smart grid, so meterings what we are using now, it is unidirectional. You get the bill from an electricity board and you have to pay it. But when you talk about smart metering as a bidirectional, then dynamic demand response and control through customer participations. Then facilitates power trading between utilities and consumers. So defining the smart grid, that is a power system made of numerous automated transmission systems, all operating in a coordinated, efficient and reliable manners. In the smart grid, a power system that handles emergency conditions with self-filling actions and is responsive to energy market and utility needs, or a power system that serves millions of customers and other intelligent communications infrastructures, enabling the timely, secure and adaptable information flow needed to provide power to the evolving digital economy. So if we see that, smart grid is basically objective at the objective, maximize the customer return on assets and operating efficiency executed by delivering the smart grid. So already you have seen these points. So this is a major comparison of power grid to smart grid. That is today grids and smart grids. Here consumers are all involved. They are non-participating in power systems in smart grid, whereas they will be involved and active participations dominated by central generations. Basically there is no private players in electricity. Basically power is supplied by central. So in smart grids, many different energy resources sorry, which plug and play companies focus on the renewables. So in the present grid, renewables plays not that much importance. As I told you, if we talk about the USA, that's California, they have put a role that 50% power should be produced by themselves. So the customers, they will have the solar power plants. So what happens in daytime while they are working office, they will sell to the grid, and night time they used to get from the grids. So that's the advantage of, if you see, that is not so far working in India. So limited wholesale markets, not well indicated limited opportunity for consumers. Focus on outage, slower response to power quality issues, later integration of operational data with asset management, responsive prevents further damage focus. So if you see smart evolutions, first we talk about automated meter reading. If you see automated reader meter, you will see in this case a system is allowed to read automated meters. Now whatever our meter is reading, this as I told you is not bidirectional. You are not getting included reactive powers. You are not getting any included the power factors. So that should be more transparent. So when our meters are more transparent, you can tell it is a, and it should read also meter automatically. That's not tampered. Automated meter management, a system is allowed to read uncontrolled automatically meters. Then if when you have AMR, AMN, then our grid will be automated grid management. A system is allowed to read and control automatically various components of the grids. So this is grid evolution, so that will become smart. Yes, sir.
Good afternoon, participants. I think Chip is having some network issue. Okay, he will join soon.
Yeah, is it audible and visible? Hello? Hello? It is audible?
Yes, sir, your voice is audible. Your voice is
Now,
audible.
yeah. So you started recap what I told you. So about the smart grid introductions I was giving you about what the smart grids. Then I was telling how to define the smart grid. Then the power system made of numerous automated transmission systems, all operating in a coordinated, efficient, and reliable manner. So basically, this power system handles emergency conditions with self-healing actions and is responsible to energy market and utility needs. A power system that serves millions of customers and has an intelligent communications, you can tell that the smart grids. So if you see a strategies focus enabling the smart grids, so as I told you, main objective is maximize customer return on assets and operating efficiency executed by delivering the smart grids. So requirements of a smart grid we have seen that basically it is self-healing, interactive, optimized, predictive, distributed, integrated, and more secure. So this is a comparison what I have told you. Basically, if you see in the smart grid, customers play very important role. They are very active. They are involved in much more. It has a lot of sensors, so it takes care of power grid problem. It takes care of every disasters. It is self-healing, and also you will see automatically it detects and responds to problems. Focus on preventive, minimizing impact to consumers. So I was telling about smart grid evolutions. First you have AMR, AMM, and AGM. Then you will see power flow versus influence. As I told you, in this system is a bidirectional and smart grid network of networks. What is HAN? I was telling when you are using IoT for smart grids, that is Internet of everything. So HAN is home area networks. In a home, you will have a lot of devices. You have computers, you have refrigerators, you have air conditioners, you have washing machines. Where you have wired, where you can use by internet, you can make it smart. You have bulbs. So all this control can be done by smart grid. That's why if you see that IoT plays important role in home automations. You have, so in that case, you have used a lot of sensors so that home automation can be done. Then AMI, that is advanced meter infrastructure networks. So in that case, we will see what happened. Every house will have a meters, you take the smart meters, that will give the demand of the house. That is the demand response. Then what happened? You have PHEV stations. PHEV stations are used to charge the electric vehicles. What is PHEV? It is plug-in hybrid electric vehicles. Vehicles can be run in electricity as well as in renewable energy. It can be a solar, it can be a hybrid, it can be fuel cell. So this is nothing but plug-in hybrid electric vehicles. Stations will be there. Then you have distribution area networks where you talk about outage management, mobile applications, distribution automations, and power quality sensors. So if we say we have seen IoT, in case of IoT, use internet in all these devices or Internet of Things by using sensors. Here also smart grid, without sensors you cannot use. You talk about power quality sensor, you talk about fault, or you talk about protections, all can be done with the help of different types of sensors. Then function of smart grid components, what are things are there? Smart devices interface component. Then very important storage component. See, we are talking about renewable energy. Renewable energy can play important role unless if you see, Unless if you are not able to store it properly, then you cannot utilize it properly. So storage plays very, very important. So what are storage you are using nowadays? You have storage technology which include pump, hydro, advanced batteries, flow batteries, compressed air, superconducting, and magnetic energy storage, supercapacitors, and flywheel, as well as associate market mechanism for handling renewable energy resources, distributed generations, environmental impact. So transmission subsystem components, monitoring control technology. So these are different components of smart grids. So smart grid functions, how it is working, you have cyber security must be there everywhere. Then basically what happens, you have bulk generations. Bulk generations should be ready, should go to the markets. Then operations, what is going to do? There is service providers are there, and operations should be a bridge between market and service providers. See, whatever there are people say, Tata is there, GML is there, Reliance is there, they produce power. So if you want to sell the power, you have to sell in the market. See, in Indian energy system, basically Tamil Nadu, it is not a horizontal approach, it is a vertical approach. You have a TLEP, which is losses is around more than 28,000 crore. So what happened there, that here you have a top to bottom approach. But in smart grid, you have a top to bottom, bottom to top approach, both sides, bidirectional. You understand? So what happened, there will be many private power suppliers who can sell that power freely so that you can get a better quality. So in this smart grid, as I told you, that IoT plays a very important role for home automations or industrial control systems. So this is the customers, you have electric power utilities, you have distribution, so you will see you have generation, then you have transmission, then you have distribution, then you have customers. So all this data should be controlled by an operator. You have a control centers where operators will be sitting here and controlling the tariff for customers and see the quality and detect the defect in the systems. So I think in the case of IoT, I was telling about the different type of communication channels that in IoT, that is wireless, Bluetooth, GP, WiMAX. So this is same thing is for smart grid. I'm not going to repeat it. Okay. So these are the communication technology in the smart grids. So this is the evolutions. Now we are going for, as I told you, 5G. So what is the difference in 3G and 4G? So you can see the speed 1 gigabyte per second. In 2003, our rate is 384 kilobyte per second. So it is slowly uploading rate is increasing, or you can download is also increasing. So you need faster. Then very, very important is what is a PMU. These devices, as I told you, in the IoT, when I am taking IoT, they are always compared with the SCADA. So can you imagine without internet, can you use PMU? So without internet, using PMU is impossible. That's why internet of, you will say everything you can tell it. So in internet of things, PMU plays very, very important role. What PMU is going to tell? PMU is going to record the voltage and current with the phasor angle at each and every substation where it has been installed with the help of GPS. You have GPS. So GPS, this provides the phasor voltage and current measured at a given substations. From there you can find out, you can see what CTPT, this is potential transformer, this is current transformer. They will get rectified output, they will be getting, this is another output, they will convert to digital for recording purpose. So PMU is phasor measurement unit in smart grid. The high speed sensors called PMU in distributed throughout a transmission network can be used to monitor the state of the electric system. In 1980s, it was realized that the clock pulses from global position system satellites to provide very precise time signal to devices in the field. A wide area measurement system, WAMS, is a network of PMUs that can provide real-time monitoring on a regional and national scale. Smart grid is the integration of new technology that allows utilities and supplies to rethink electric grid design and operations. So PMU will see what basically it is going to do, what the applications of PMU are there. This can do the adaptive drilling, installing the prediction. See, from voltage and current, you can get lot of information. You can find out what system is stable or unstable. You can get the data, that is state estimations. You can improve the control systems. If there is a fault can be recorded. It can be disturbance recordings. It can be transmissions and generation modeling verifications. You can do wide area protections. You can do fault locations. So these are, you can see here, voltage and currents measured at each substations. So there will be a phase difference between substation 1 and 2. These are GPS, which gives magnitude and phase angle. What happens if we say this is actually a PMU based wide area multiplication of ones. So you have PMU at different area, at different substation PMU can be installed. That can be monitored by wide area monitoring systems. You understand? That should be data should be monitored so that you can find out system is stable or unstable. So always there is a comparison between SCADA and PMU. So in terms of resolutions, you have PMU have very good resolutions. SCADA measure only magnitude, whereas PMU measure magnitude and phase angle. Always is to compare one is MRI scan, another is X-ray. So which is X-ray nothing but SCADA, MRI scan is PMU. So depending on applications, you can go for PMU. PMU may be costlier than the SCADA. Each requirement is there, you can go for PMU. In SCADA, there is no time synchronization. In PMU, it is there. In total input output, there is 100 plus analog and digital. Here you can have digital, analog, local. So basically, it's wide area monitoring controls. Here it is only used for local area. So these are the benefits of PMU: real-time monitoring, both disturbance analysis, adaptive protection, power system distortions. Then we will be talking about smart meters for a few minutes, as it's very in present scenario. Smart meters play very important role. What do you design from a smart meters? Which provide digital results in quickest possible time, deploy appropriate technology at affordable cost for today and tomorrow. So why does it take to adapt and growing change management issues, system versus standalone equipment? So in terms of need for distribution management, see at the customer side, at distribution sites, what are the information you are expecting from a house? You will be knowing about the quality of the power, revenue, how to protect it, customer relationship, transfers and vacancies, managing credit, collecting cash, customer billing. So these are the information you will see you are going to get smart meterings. Can you imagine what meters you are having now? Are you getting all this information at present? Answer will be no. Because we are not able to get all this information through present meter. That's why present meters should be replaced by smart meters, which is very helpful for distribution management, that is distribution systems. So smart meters records consumptions in intervals of 30 minutes or less, communicates information at least daily back to the utility for monitoring and billing, enable two-way communications, provides online update to the users through web or in home display to help efficient energy usage and reduce bill sensors for smart meters. So key drivers of smart metering in India is reduce theft, improve customer services, it integrates renewable, if you say net metering is that. If you want to transfer any energy to the grid, it can be the net metering. And it will helpfully supply power 24/7. Because now what happens, you don't have the load in a house. So they can take more load than power, maybe then the power sharing will be there. But in smart meters, if they consume more energy than the rated, then there will be alarm will be there. Then there may be a signal to the utility to make what they use more energy. Utility operations benefited by adaptive smart meters, are the benefit you can get. So understanding the root cause of ATAL, that is your automated transmissions and commission losses. So why we are not able to implement the smart meters? As I told you, it is very costly. If the general meter is 2,000 rupees, smart meter cost 10,000 rupees. Unless government is making awareness, then you cannot make it. And our systems are for long time, there is no change in the transmission lines. So due to age of the networks, efficiency is very less. And geography, you have thunders, you have cyclones, so you have flood. So that also affected our system is not so much robust. then sharp spikes, voltage variations. So you have high ambient temperatures, dusty humidities, poor engineering practices. So these challenges in Indian context you have to overcome and you have to use the smart meters. Technology alone cannot solve problems. See, there are for each problem there are solutions. But can you adapt the solutions? You cannot adapt because it depends upon the cost effectiveness, total cost of ownership, sociology of technology. People should be ready to change their attitudes. They should be ready to adapt the changes. Then you can make it change. So key message is that you will see after the root causes of losses, as you know that total losses in transmission distribution losses are around 30%. Only I think Tamil Nadu is having less losses, that is coming around 18%. So overall it will be 30%. So losses if you will minimize, it is indirectly you are generating more energy. So this smart grid can deliver what? Plug-in hybrid electric vehicle. This smart grid diagram will be like this, where each house will have the power production, maybe solar, maybe wind. You can see in the pictures. So these electric vehicles and plug-in hybrids, they play a very important role. So we are talking about IoTs. So you just think to control you have to control mechanisms. You need sensors, you need IoT. The case of electric vehicles and hybrid is another component of the smart grid systems. Smart vehicles. PHV, as I told you, this is PHV's plug-in hybrid electric vehicles. It is to reduce the dependence of fossil fuels and carbon emissions. The next is vehicle to grid. So what you can see, whenever there is a abnormal time, there is power cut is that you can get power from the vehicles. Vehicle can discharge power to the system. But normal time vehicle can be stored the power. That is also possible. Business model for smart grid, smarter electric system you can see here. Past use the landline phone. Now everything can be by internet. So you will see this IoT what I'm talking. You can see here the application of IoT. The internet of you can tell you everything that internet of things. You see here earlier we are using landline. Nowadays no landline is that we are using broadband, Wi-Fi or 5G, 4G. You can show everything is controlled by internet. Well, everything is controlled by internet. That's why it is now. You can tell the internet for everything. The smartening of electric system is an evolution process, not a one-time event. This evolution takes a lot of time. It has happened all of a sudden. See the present system and future system. Future system, you see, you are more giving emphasis on the control center. You have energy service provider, you have electric vehicles, you have distribution control centers, you have industrial customers, you have commercial customers, you have residential customers. So for all these customers, data or your load pattern will be different. That can be managed by demand management systems. The smart grid architectures. In a traditional grid, where you don't find the renewable energy, you can see here carbon dioxide emission around the world. So more carbon dioxide will be there. If you see, it is more in China. Then if you see America, it is 16%, China is 28%. So the rest of the world is around 19%. So Asia, if you see, this is a percentage. So now if you see, as you know that total power whatever you producing, it is coming around at 31st December. Last year it was 360.78 gigawatt. So if you see India has installed power capacity. So out of that 63% are produced by thermal. And if you see there is a challenge, I think our former president Dr. Abdul Kalam, he told that by 2020 you should achieve 25% of total energy should be produced by renewable energy. Now we have achieved 23%. I think now by this time we have achieved close to 25%. So we are in the right tracks. So the wind installed capacity of India 37,505 megawatt. Solar installed capacity is coming around 32,000. Now at present I think solar has crossed the wind. So this is a future grid framework. Future grid will be looking, you can see here, future grid will be looking like this. So I will be talking next slides. You are going for a DC microgrid. So there is a lot of talk is going on. Now, presently, if you say you are in a AC. So, what is a microgrid? Microgrid is a part of grid which is having its own resources. You can see here you have a magnetic microgrid, you have a DC microgrid. DC microgrid have a storage, that is supermagnetic energy storage is that. You have electric vehicles, then you have energy storage which is bidirectional, then you have solar. The same source is solar, you make it a DC microgrid. Then you have the DC bus is that, DC is connected to AC converter, then supplied to commercial load, industrial loads. You are converted to AC. Similarly, you have a AC bus, then this is magnetic microgrids, AC to DC converters are. This is the future grid framework where you can have DC microgrid as well as AC microgrid. Here you are integrating renewable energy. So you can see here these are renewable energy are integrated. So now this becomes a smart grids. Okay, in smart, if you see the previous diagrams, you are not having any renewable energy. You are only having the conventional energy. Now you can see in these diagrams, you have the renewable energy, so grid becomes smart. You can the grid becomes smart. So power flow will be bidirectional. So these are different part of the smart grids. I think we will go through the building blocks of smart grids. So as I told you, large scale that what is a microgrid? Microgrid, as I told you, is a part of the smart grid. This is a microgrid where you have DG, you have central hydropower stations. Then you have, if you see, small storage are there. The electric grid, the thermal grids, the smart grid applications. So if you see here, this is a customer management smart grid, how to manage the customers. So integration of computer intelligence into power grid. So very important topic is this artificial intelligence that plays important role in the smart grid. This is the micro smart grid. You can see this is the micro smart grid where you have DC power, AC power, and information is basically going to DC to AC and DC to DC. You can see this is a micro smart grids. Okay. Now if you see, basically now I will come to the first part of my talk, that talks about the what do you mean by a smart grid. This is a diagram of the smart grids. If you see here, what is S stands for signal processing, state estimations, stochastic generation, and self-billings. M stands for monitoring, that is WAMs, multi-energy carriers, multi-variable optimizations or control, mixture generations, market enablers. Then you have A stands for adaptive hierarchical control, augmented power transfers, affordable solutions. Then you have R stands for robust, response to demand, reliable. Then you have renewable energy sources, real-time control, reduce uncertainties. Then you have T stands for transcontinental, tailored for individuals, tolerant to behavior patterns, trade-off analysis. So if you add all these features to the grid, S, M, A, R, T, these are the different features which are adding to a grid, then grid becomes a smarter. So your conventional grid, how it becomes smart? Add the features of signal processing, monitoring, adaptive, robust, and your trade-off analysis. If you add all these features, then the grid becomes smarter. So you can say smart grids. So smart grids are prerequisite to reach political targets such as environmental, efficient energy, and secure supply. Improve the smart grids and evolutions of the existing grid. Hello. So if you see here, smart grid, I am concluding here. I will be going to the next slides that talks about the I'll be presenting another slide that talks about the renewable energy, what is the importance in the present grid. Then we'll talk about DC and AC microgrid. So if you see what I've seen about the smart electric grids, which is traditionally so this is you have seen already what is a smart electric grids. Just now we are discussing on a smart electric grid. So now if you see so if you see here, these are we have seen smart grid is an electricity network with RAD ICTs. So if you see here, it should be intelligence, then should be efficient, and should be accommodating. Smart electricity should be motivating, opportunities, quality focused, resilient. It should be green, slowing the advance of global climate change. This is the smart grid definition. Smart grid should like this. So this is a comparison. It's a digital, existing electromechanical, it's a hierarchical, it's a network, few sensors, more sensors, self-monitoring, self-healing. So this is smart electric grid. So already I talked about wind energy status. Let us talk about the wind energy status in India. So this is the old data. I have shown you the recent data. This is all about the wind turbine power versus speed characteristics and maximum power point tracking, how to get in case of wind. I think we will talk about the DC-AC microgrids. We'll leave this one. Yes. So basically if you see this wind energy system, when you integrate it, what are the problems you are facing? Wind flows always varies and depends on weather conditions. Because of this great integration of wind energy conversion systems, it can affect the power system negatively. This intermittent and diffuse nature of wind power introduces new factors of uncertainty on the power system operations. Technical challenges with integration of large wind farms to the grid. When you integrate the grid, as you know that wind speed is not constant. When wind speed is varying, what happens? Output voltage is not constant. So, what are the challenges we are facing? Impact on system securities, there will be more chance power will imbalance, impact on reserve management, impact on power system voltage. As I told you, voltage will be changed. Then we have impact on power quality, that is about harmonics will be there. As you know that when you use wind or use solar, you are in the converters because that voltage is fluctuation is there. So to have a constant voltage, you use the inverters, correct? So when you use inverters, you are using thyristors. You are in the when you use these control devices, inverters or your rectifiers, there is a lot of chance it may create harmonics. You know the harmonics are the on-desired part created due to the non-linear devices. So these thyristors, diodes, they create a lot of harmonics. So whenever talk about the wind farms, they will be creating flickers, they may create harmonics, they may create voltage dip. So impact on power system stabilities, that is you talk about transmission planning. Impact on first point is impact on system security. What happens to system security when a wind farm is connected to a grid? Security of the systems means ability to contribute to both the frequency and voltage control in stabilizing the system following a disturbance. When disturbance is there, system security means what? See, when you do synchronize a grid to the wind farms, as per a synchronous rule, voltage and frequency should be matched. But due to change in speed, there is a possibility voltage and frequency may not match. So it may affect the system securities. They must be able to ramp or ramp down. They must be able to ride through disturbances. They should be able to operate in the island mode when supply from grid is lost. You understand? So that they must be operated in the island mode also. So island operations will change the power flow, maintaining the power balance is required after island operations. When you do power you are getting from the grid, then things are different. When grid is not supplying power, there is a problem in the grid or your system has a problem, you work as a island systems. So when you do work as island systems, your power management will be different. When grid is connected, power management system is different. When you do island, your power management will be different. So here you see the microgrid. It's a microgrid connected to the grid. So microgrid has its own resources, as I told you, PV and storage. It's a hybrid, okay? So they will be injecting power and load. So microgrid may generate more power. It may also supply to the grid. But if it is island, it is not connected to the main grids. Impact on operating cost due to power imbalance. The system must maintain a balance between the aggregate demand and total power generated by all the power plants feeding the systems. Wind speed cannot be predicted with accuracy. Consequently, utility planners and operators are concerned about the variation in the wind outputs. Conventional power plants require to deviate from operating points that are chosen to minimize total cost of operating the entire system. A penalty cost is often attached to the deviation in the schedule and actual use of the grid. This will increase the operating cost of the system. The impact of wind power on reserve management. A system of high wind power integrations will expand the reserve capacity due to the variability of primary sources. Mostly conventional power plants are expected to provide for that variabilities. Due to more variable nature, it has effect on both the operational cost and ancillary services cost of the system. An extra reserve of 3 to 6% of the rated capacity of wind plant is required in a 10% wind integrations and 4 to 8% application for 20% of wind integrations. Impact on power system voltage control. The nodal voltage distribution on the power system network must be within the acceptable limit. The reactive power contributions capability of a power plant determines its nodal voltage control. So what I am telling, voltage control is very, very important. If you want to maintain system stable, you must be able to maintain the voltage properly. Nodal voltage should be properly, because you know that most of the energy control systems make use of induction generators, which are not capable of injecting reactive power to the grid. So it is very, very important. You must be capable. You will see your HPDC sessions. What happened? You have a SPC or you have a sound reactors. Why you use sound reactor to SPC in the HPDC sessions? Because they inject the reactive power to the grid. You know, reactive power is very much essential. If you don't get reactive power, you cannot maintain the voltage balance. To maintain the voltage balance, reactive power is required. You know that voltage is fluctuation will be there, and there may be a voltage drop will be there. So to maintain the voltage balance, reactive power you must inject to the grid. Impact on power system voltage control. Variation in the steady state voltage. Relationship between voltage gradient and the flow of active and reactive powers on a radial distribution feeder can be expressed in terms of RP plus SQ by V, where if you see reactive power generations, then reactive power absorptions is for negative. Rx is the feeder resistance and reactance. P2 is the active and reactive power. Plus minus depend upon leading and lagging. In case of transmission line, X by RSP is significantly more. However, in case of distribution line, it is less. It can be said that active power has major effect on the voltage profile in case of distributions, that is in the low voltage systems. Whereas reactive power transfer is dominant factor in case of transmission. See, you talk about when you transmit a high voltage, that reactive power is very, very important. That's why you will see when you transmit low voltage, that active power will play important. This is the active power flow, already you know this one. Impact of power from voltage. Few examples is a large wind farm, say 400 megawatt connected to 275 kV networks. The network impedance is relatively active. This allows the exchange of large amount of active power with the relatively voltage down. However, exchange of reactive power between grid and wind farm affects the voltage. That is very, very important. Generation embedded distribution networks, you can see the diagrams of different diagrams. Low voltage variations during transients. This happens because of fault on the transmission lines. Severe grid disturbance such as huge voltage peak caused by short circuit fault can lead to generating units disconnected from the grid. This may cause instability in the grid. That is very important. See, instead the grid is happened when there is a short circuit fault. According to new grid code, wind energy turbine must stay connected for the fault. They must be stable throughout. This capability of wind generator is called low voltage right through capabilities. Few examples are that for protections and fault right through capability of double shot induction generators. Then PMSG. These are the diagrams how they have gone through fault right through requirements. Impact on power system voltage control, high voltage. Impact on wind power and power quality. Very, very important. Just 1 minute. So if you see this, as I told you, power quality is plays very important roles. So there you will see wind power is basically compared to solar. We are talking more about the power qualities. So जगह शुरू करते हैं क्या? हाँ सर आएगा तो उसको बोल दीजिए मैं एक टॉक में हूँ मैं 3:30 में ज्वाइन करूँगा ठीक है? सर को बोल दीजिए ठीक है? ठीक है Any problem call me okay thank you. So if you see the power qualities, deviations. So what is power quality? That is quality power. You need voltage and current or frequency should not deviate from the rated value. Deviation from nominal signs of voltage or current waveforms in power system networks determine the quality of power transmitted in the grid. So what are problems you may expect? There may be harmonic distortions as I told you while using the converters. There may be flickers because voltage may change very frequently. There may be voltage imbalance, there may be voltage surge and voltage swell. The level of tolerance of power quality depends on the kind of load installed by the customers. That's how sensitive the load is. Poor power quality could lead to losses in the grid. When now poor power quality, there may be a chance, suppose that a flicker is there, what happened? There may be a chance that your equipment may get damaged. So indirectly will be losses to the grids because if is power fluctuation is there, most of the equipment may burn, it may damage. Malfunctioning of the ATAL equipment and even a loss of synchronization that could lead to the network failures. Fixed speed wind turbine produce power pulsation due to shear effect and this could result in a voltage fluctuations that could cause flickers on the grid. Generation of harmonics. At the generation level, sources of harmonics include power unit interface and FACT devices. It injects the harmonics into the systems. Others include adjustable speed drivers, generator speed controls, speed installation. They could cause distortion to the voltage and current waveform of the power systems. So harmonic increase the line losses and cause excessive heating because you know due to harmonics your total current is increasing because you have apparent current, you have the harmonic current. So if you add current will be more. When current is more, that's the excessive heating of the equipment, which decreases the lifetime. The limits for system voltage distortion are 5% for TLD and 3% for any individual harmonics is stipulated by IEEE 519 standards. As per IEEE 519 standards, your distribution size harmonics should not exceed more than 5%. So this harmonics plays a very, very important role, and this is mainly created due to the wind farms. Voltage dip could occur when there is a large load such as motor startup, transformer energizing, capacitor energizing, momentary overload, or a fault in the system networks. Voltage dip is considered as a drop in power voltage to level below 90% of nominal voltage or no longer than a minimum. Due to this effect on sensitive equipment and industrial processes, it is a common and serious type of power quality disturbance problems. Impact on power system stability is very important. Stability is nothing but ability of the system to remain in the synchronism after a disturbance. Power system stability investigates how a power system responds to a disturbance. For an example, frequency changes because the generator trips or a load is switched in or disconnected. Voltage drop due to a fault. Now with variable speed wind turbines, you have to deal with wind generators, either squirrel case or DFIG or PMSG, having power voltage interface. That is very, very important because unless you don't have power voltage interface, you cannot have the constant output power at the end. Wind generators with spark electronics interface provide very less inertia. Even though variable speed wind turbines do not contribute to the system inertia, the inertia can be using additional control loops. Primary frequency support by wind turbines can be achieved by following methods using deloaded operation of wind turbines, incorporating deliberate inertia response in converter control. This is a deloaded operation of wind turbine systems, how it becomes stable. Deloading means shifting wind turbine generator's operating point from its maximum power point to the reduced power point, thus creating some result. See, this is deloading. You see here, this is the maximum power points. We are operating at this point. So that, if you see, you are creating a reserve so that it should not operate at the peak. The wind turbine generator may be deloaded by shifting the operating point towards the left point C or right point B of the maximum power point A. A is the maximum power point, either you can operate in C or you can operate in B. There is no frequency here, increasing the generation margin thus created. The WTG output can vary between P del and it can vary from P del and P max by varying in rotor speed between omega del and omega maximum. Impact on power stability is what impact. Inertial response is converted in converter control. The resilient capacitors of converters store considerable amount of energy during normal operation. Some of this energy can be extracted to create inertia response. The control action is achieved by changing the reference voltage of DC links in delayed manner that is proportional to the frequency deviations. In case of variable speed wind turbine, the sensitivity of the power turns converters to overcurrents, the transmission planning, then how to mitigate strategy for wind energy converter systems integrations. An acceptable integration level of wind power has not been defined. No particular definition has been given so far. However, by adapting and improving the various mitigating strategies, some of the integration challenges can be alleviated and higher integration level can be achieved. Some of the strategies are geographical locations, use of smart grids, improved energy storage technology, improved wind forecasting techniques, use of FACT devices. These are geographical location. The correlation between the fluctuating primary resources of different sites decreases with the distance between the sites. See, you want to find out where wind can operate healthy and wind speed will be almost remain constant. That location is very important. Study also revealed that 10 or more geographically separated wind farms connected together have a reliability about 30 to 47% of their average output compared to a concentrated located wind farm. This is very, very important. Use the smart grids. See, we use the information and communication technology (ICTs) based network that will allow bidirectional flow of power. So, what happened in whenever you should not depend upon only the wind farm, you must have other source so that power can flow bidirectional, so it can maintain the balance. Smart grid allows the transmissions of wind power from a site of favorable generation to a place of high demand over a long distance. Mostly practiced with the high voltage direct current lines. If we use HVDC line, what happens? It has a inertia, it has a capabilities of injecting reactive power. Using proper wind forecasting and load demand management technique, the imbalance between generation load can be decreased. Use of improved energy storage technology, that is very important. So you can use electric vehicles as a storage techniques. Will increase the indication level of wind power. Battery of EV is charged at night when the cost of power is low and there is excess power from the wind generators. That's very, very importance of electric vehicles. Use of FACT devices can be used, SPC, STATCOM, they inject a lot of reactive powers and they can use also, STATCOM can also mitigate your voltage flickers. You talk about shafts, fuel, they can do it. This is a given of STATCOMs, I'm not going to details. So now we will talk about the power management of DC microgrid. This is the last part of the talk. What is DC microgrid and how power can be used. So microgrids, as I told you, microgrids are low voltage distribution systems containing loads, distributed generations, storage devices, or controllable loads that can be operated in a controlled, coordinated way, either in grid connected or standalone mode. Microgrids can be AC or DC depending on the connection of sources and loads to the common bus. Extensive research work has been carried out in the last few decades for smooth operation, control and protection of AC microgrids operating either in grid connected or island mode. In recent years, DC microgrid system has attracted increasing popularity over AC microgrid due to numerous advantages. The DC microgrid is more reliable and has higher overall efficiency and low maintenance cost due to the requirement of single stage converter as compared to two stage conversion AC microgrid. So what happened? When you talk about microgrid, in microgrid we'll see, you talk about solar. If you are using AC microgrid, DC microgrid, then power conversion stage is only one. But in DC AC microgrid, power should convert AC solar, DC solar, solar should convert to fixed DC, then you have one more, if you see, you have one more inverter which can give you the AC. So these are two-stage conversions. The DC distribution systems can be well operated in standalone operation during the occurrence of fault in the grid. And the DC microgrid does not face any grid synchronizations. That is very, very important. See, when we talk about AC system will basically depend on the frequency. So grid synchronization is a very challenging thing. Synchronizing the grid in AC will be more difficult and controlling also difficult. Neither the needed grid side frequency or phase control. That is the main important is in DC microgrid you don't have the frequency control, not required phase control, which is required very much in the AC grid. So what are the operational challenges in DC microgrid? The DC microgrid has the following major operational challenges needs to be taken care for its smooth operations: optimal power sharing among different renewable sources, connected DC bus system during system contingencies, DC link voltage control within permission limit, power management, that is stability, fault tolerance, design of suitable converters for DC microgrids. So this is general structure of DC microgrid where you have PV cells, wind turbine, then you have fuel cells, then a battery, electrolyzers. So you have the DC-DC converters, you have AC-DC converters, you have DC-DC converter, DC-DC converter, you have DC-DC converters. Then this is the DC grid where you have the DC link capacitors. Then it will go to the DC load. Okay. This is the structure of DC microgrid. So, sir, what are the motivations? Because several methods are available in the literature for DC link voltage control and power management in DC microgrid. Purpose of most of the schemes are evaluated considering limited varieties of renewable energy sources and energy storage devices operated either in grid connected or island or line fault conditions. The non-deterministic character of renewable sources and land and loads in standalone DC microgrid imposes difficulties in achieving the power balance. Power balance is difficult. So if we see here, I can show about here what is the main researcher, that is how power management control strategies for DC microgrid with the storage devices. You can see here what the objective is to develop an adaptive control strategy for a hybrid DC microgrid system combining variable generations and energy storage devices which can ensure effective power management and DC link voltage control under system contingencies. So you can see here, this is a PV cell, you have a maximum power trackers, FDP techniques, then you have a PMSG, current magnetic field signal generators, then you have a fuel cell, you have electrolyzers, then you have batteries. So all will give, we'll see this is a 250 volt DC. So PMSG will give you actually AC, then you have rectifier so that you can convert to fixed DC. So if you see DC, what happened? Here, if you see all this case, this is a single stage power conversions. Okay, but if you want to have a AC microgrid, there will be two-stage power conversions. You can see here, you have PV, you have PMSG, you have fuel cell, you have electrolyzers, you have batteries. Devices are connected to your DC microgrid. Center DC boost converter with controllers. Then it is connected to the utility grid with 660 volt DC bus high voltage level. Then you have a point of common coupling. Then you have a DC to AC converters. You have a DC to AC converters. You have an inverter controller. You can see these diagrams. 1 minute, excuse me. So if we see in these diagrams, we have DC microgrids, and is it audible? Hello? Is it audible?
Audible. Audible. Yes, sir.
Okay. So this is diagram about DC microgrid. So very important is nowadays you know a lot of going on AC and DC microgrid. Made yesterday Professor MP Padi from IIT Roorkee, he was telling that they have excellent laboratories for microgrids, and they have the first laboratory in India. They have established in the area of microgrid. They have also DC microgrid. Even I met also Dr. Siva Kumar, who is right now working in IIT Hyderabad as associate professor. He told their job is they are working on DC microgrid, so that their future plan is all these substations, all these stations can operate in DC. So they are working for 48 volt, because if it's on domestic or home appliances, how AC can be replaced by DC? It's a difficult challenge, but difficult task. But nowadays a lot of research is going on to work in the DC microgrid. As you know that losses will be less and it handle low voltage. You understand? AC it handle with low voltage, and also if you see basically losses will minimum and maybe cost maybe less. If all we generate the sustainable energy, then it may have important role. You can see in this diagram, you have DC to AC converter. Then it is connected. Filter is connected to the transformer, through it is connected to the main grid, utility grid. So control strategy employed for PV cell. These are the normal equations for PV cell. Proposed control employed for each system. You have PV, you have PMAC, you have fuel cell, you have electrolyzers. For each system, you must use the control strategies. Fuel cell, electrolyzer, all those things, so that it can be controlled properly. I am not going to detail about the controller, about the subcomponents. That is your Takaishi fuzzy logic controller, your mountain time logic controllers. So this control strategy employed for grid connected island mode of operations. This is one of the research work that I am showing you to have an idea how research can be done in the area of microgrid. If we see most of the whatever talk I have given today, initially I talked about the smart grid, why it is important. As your FDP based on IoT for smart grid, so you might have seen my talk. Basically I talked about smart grid tools. They are known as your PLU or WAMS or HAN or PAN or you talk about LAN. So these devices cannot be used without internet. Whenever you use internet, you are telling it is internet of everything or internet of things. Correct? So smart grid is just a very important part is smart meters. Smart meters, what using nowadays, that is not smart meters. So these smart meters cannot use without internet. You talk about smart home automations. You might have, I think, some lectures by home automations, or you talk about your data management system, that is DMS. So these things, wherever you talk about smart grid, that IoT plays very important role. And this smart grids, without renewable energy, you cannot think about the smart grids. You understand? You talk about you think about the plug-in hybrid electric vehicles or vehicle to grid. So all those things, wherever application is there, renewable energy plays very important role. Or you can talk about the sustainable energy plays important role. So there we will be discussing about, unless you don't know the control strategies, then integrating to the meltware will have lot of problems. So here we have discussed the different control strategies. What are the impacts of large wind farm to the grid? So you have seen they may have diff, they may have shack, swell. This can be also solved by using the fact devices. That is your STATCOM, SBC, that is your UPFC, QPSC, TCR, TCSC. There are a lot of fact devices are there which can be used to improve the system voltage. So I think if we see all presentations, so we are talking more about the electric vehicles. So now I think this is whatever topic is that is IoT for smart grids. So now I can conclude it as I have, I think, I am organizer on FDP, that is on application of different control techniques for fossil energy. So it is going to start. So if you have any questions, you can ask me now. Santi madam, there are many, audience have any questions, any queries, they can ask me. Because I am going to be writing fast, as there is some network problem in between 3 times.
Posted your query in chat box.
Yes, somebody asked that you use for DC microgrid. See, basically, using the MATLAB. See, you might have seen the simulating diagram that I have shown the presentations. They can be solved by only using the MATLAB. I'm happy to tell you that next week we are having a. Yeah, yes. शुरू में मेरा अभी 2 मिनट लगते हैं और चल रहा है उसका रिकॉर्डिंग शुरू कर ठीक है यू स्टार्ट द रिकॉर्डिंग ओके सो व्हाट आई एम टेलिंग देयर इज सम क्वेश्चन that what software you should use for this DC microgrid. This software is basically most important is use the MATLAB. In MATLAB you can solve it, and there are so many subcomputing technology are there for utilities. Okay, you can use any subcomputing technology depend upon their problem. Yesterday we had a speaker, Dr. Tanay. Sir, he was telling me they can use there are a lot of AI techniques are there which can be used to solve the problems. Any more questions there?
Participants, any queries? Kindly post in chat box.
Yes.
Yes or no? Sir, no queries. Sir, thank you, sir. Thank you for accepting our invitation.
I must thank you. Yeah, 1 minute. I must thank you for your, I think, inviting once again and introducing me. I must thank you, Dr. Jagdish Kumar. I must thank you, Head of Department, Dr. Annagan. I will all the participants who is present here because after long attending lecture is quite difficult. So I must thank to them and thanks to Sairam Institute of Technology for giving this opportunity. So real thank you to all of you. So you can contact me at any moments. Thanks to all. Thank you, madam.
Thank you very much, sir. Thank you for spending your valuable time, sir. Thank you very much, sir.
Thank you, madam. Thank you.
Thank you, sir. Thank you, sir.
Thank you.